In this video, we're now going to learn about the process of absolute dating. Relative dating is where we spend time learning about how we can compare the rock ages of different events and layers by just saying simply who's older and who's younger. Absolute dating is different because it puts an actual number to it. So specifically, absolute dating is the process of determining the actual age of a rock or fossil through radioactive dating techniques. So here we have all of these rock layers, and now I'm very confident that you guys can tell me where the older rocks are and where the younger rocks are. But now with absolute dating, we can say confidently, for example, that that layer is 350 million years old. Now we're putting a number to these ages, and that's absolute dating. So how is absolute dating done? This is going to be a very, very brief overview, but I think it's important to understand. So first thing scientists need to do is they have to take what they call sediment cores. They're essentially sticking something similar to a pipe deep into the ground, and they pull out a core of all the dirt and sediment and rock that they can get from that specific core sample. They take a slice, a small part of that core, and what they do is they look at what makes up that rock. They look under microscopes and other types of analysis equipment to see what types of minerals and elements exist within those samples. So here's an example of the periodic table of elements, and some of these elements can be found within those core samples, and scientists can use that information to figure out what was in it, and ultimately they can figure out how old that sample is based on the elements that are within that sample. So in order for us to understand that a little bit more, we have to learn a little bit about something called an isotope. Now when you get into chemistry in a few years, this is going to be a big part of your class, but for now, we're going to keep it simple. An isotope is simply a different version of an element. Now, most elements on that periodic table have several isotopes of their own. So let me explain this a little bit further. You know that carbon is an element, but carbon can come in different forms. There's a carbon-12, a carbon-13, and a carbon-14. And those different numbers represent different masses of the carbons. Now, isotopes of the same element, all these isotopes of carbon, they all have the same number of protons and electrons, but they have different mass numbers, and therefore these different isotopes have different physical properties. Carbon-12, 13, and 14 are all very different from one another. Even though they're all carbon, the fact that they are isotopes of one another makes them have different properties. Now, going forward, how does this still tell us the age of these rocks with absolute dating? Well, isotopes can either be stable or unstable, and we're interested in the ones that are unstable. Because if you're an unstable isotope, that means that isotope can go under radioactive decay, which causes that isotope to break down into atoms of other stable isotopes. So let's look at an example. This is the symbol for carbon-14. Carbon-14 is an unstable radioactive isotope. Carbon-14 over time, because it's unstable, it's not going to stay carbon-14 for the rest of its life. It's going to turn into nitrogen-14, which is what we call a stable disintegration product. Carbon-14 will always turn into nitrogen-14. Now, the process of radioactive dating. It's using this idea of unstable isotopes to try and figure out the actual age of a sample. What we need to understand is these isotopes that are unstable, they decay at a regular rate. That essentially means it breaks down the same amount, always in the same amount of time. It's very predictable. And this allows scientists to figure out how many years it took for that isotope to decay, and they can therefore determine the age of that sample that they find. This is how scientists figured out the age of the Earth. This is a picture of a meteorite sample. Meteorites have undergone the process of radioactive dating, which allowed scientists to figure out that Earth is 4.6 billion years old. This technique of radioactive dating can also be used on bones. This is an example of a human skeleton, and we can figure out how long a skeleton or any other fossil with bones have been around because of this process of radioactive decay. So if you ever wonder on these crime shows, how did they know exactly how long a dead body was in a particular environment? This process is used for those types of scenarios as well. So again, how can we figure out for something breaking down of an unstable isotope, how does that still tell us the age? Well, that brings us to the biggest part, the concept of something called a half-life. Every radioactive isotope, such as carbon-14, has a different half-life. A half-life is the time required for half of the atoms of that unstable isotope to decay. On the front cover of the Earth Science Reference Table, you should see this chart, radioactive decay data. We have examples of 4 different radioactive isotopes, carbon-14, potassium-40, uranium-238, and rubidium-87. Each one of these radioactive isotopes has a different half-life. And again, the half-life is how long it takes for that isotope to break down by half. So for example, if you have 100% carbon-14 to start, that carbon-14, for that to be cut down to 50%, half, it takes 5.7 times 10 to the third years. It will always take that long to be cut down by half. And as you see, the other radioactive isotopes have a different half-life. Now, since these half-lives are expressed as scientific notation, I want to take some time to make sure we understand the process of how to convert from scientific notation to standard format. So if we have the example for carbon-14, 5.7 times 10 to the third years, that's the scientific notation format. In standard format, that number is 5,700 years. Now, if you're unsure how I got to that, I'm going to show you a little bit trick. A lot of students think that the 10 to the third power means you add 3 zeros to your number. But you'll notice that 5,700 doesn't have 3 zeros. That's because the 10 to the third, that 3 in the exponent means 3 decimal places. So take a look. If we were to move this 3 decimal places, we moved 1 decimal place, 2 decimal places, 3 decimal places, you fill in those remaining loops with the zeros, and we get to 5,700 years. Let's just look at one more example. Here we have a larger number, 1.3 times 10 to the 9th years. In standard format, that's going to be 1,300,000,000 years, or you can also simplify that to 1.3 billion. That's a really long time. Now, let's see how we can convert this. Remember the 10 to the 9th. That exponent number 9 does not mean 9 zeros. It means you're going to move 9 decimal places. So we move 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we fill in the remaining loops with the zeros. And we end up with the number 1,300,000,000 years, or 1.3 billion. So I want to end today showing you an example of carbon-14. I'm going to start off by reminding you that the half-life of carbon-14 is 5.7 times 10 to the third years, which is essentially 5,700 years. So here we have a graph that's showing the decay of carbon-14. I want to point out that on the x-axis we have time, and that time is expressed as 10 to the third years. And then on the y-axis we have the radioactive carbon-14 measured as a percent, so the amount of carbon-14 that we have. So let's start with time 0. So let's say right now, no time has passed. We end up with 100% carbon-14. That's where we're always starting with, 100% carbon-14. But after 5,700 years goes by, now we have 50% carbon-14. Because remember, for carbon-14 to be cut in half, to go from 100 to 50%, it always takes 5,700 years. Well, time goes on. We get another 5,700 years to go by. So in total, we have gone 11,400 years. We're left with 25% carbon-14. Because when we went from 50 to 25%, we cut that in half. That took another 5,700 years. And we end up with 25% carbon-14. Let's go another 5,700 years. So in total, we have gone 17,100 years. That carbon-14 is cut in half again. From 25%, it cuts down in half to 12.5% carbon-14. So what I need us to understand here is every time carbon-14 is reduced by half, another 5,700 years goes by. Doesn't matter how much percent it has, to cut in half every time always takes 5,700 years. So this is the first video among many. I'm going to be breaking this topic down over the next few lessons to make sure we understand. So don't worry if you're feeling a little lost right now. You will get there. But for right now, this is all we're going to build on for today.